Alright, let's take a look at exit slip 19 where we were asked to solve a system of 3 linear equations, 3 unknowns. Our technique that we've discussed regarding this type of system has been to eliminate one of the 3 variables basically from 2 equations at a time so that it becomes a system of 2 equations, 2 unknowns, which we've worked with in the past. So let's just start. I'm going to number my equations to make it a little easier to refer to. So I'll call them equations 1, 2, and 3. And then we can decide which variable we think would be easiest to eliminate. Again, we don't all have to decide on the same thing. But I noticed kind of quickly between equations 1 and 2 that eliminating x would be really easy if I just add those 2 equations because I have an x and a negative x. I don't see any other variable that looks quite that nice in terms of the first 2 equations. And then I could grab maybe the second and third equations with a little multiplication and eliminate x as well. So I'm going to go ahead and work to eliminate x. I know in the video that you probably recently watched, we chose to eliminate z in that example. So again, it doesn't matter as long as you're consistent in eliminating the same variable from 2 equations. So let's go ahead and write what we're going to do. Let's show adding equations 1 and 2 for our first step here. Add 1 and 2, and just so we don't forget our goal here, our goal is to eliminate x. And then we'll make sure we eliminate x another way in a moment. So carry down equation 1 as is, no changes needed. Carry down equation 2 as is, no changes. And let's go ahead and add those 2 up. So the x's cancel. Looks like a negative 2y plus 3y is just y. 3z minus z is 2z. And 9 minus 6 sounds like 3. So there is what I'll call our 4th equation. So that's going to be one of the equations for my system of 2 equations, 2 unknowns. We're going to do kind of a similar story now with another set of 2 equations. So let's go ahead and write directions again. Let's show adding, and let's just grab our second and third equations. So add equation 2 and equation 3. Hopefully you're thinking, wait a minute, we got to change one of those because you're right. But again, our goal will be to eliminate the same variable of x. So that's the important thing. Make sure in both instances you're eliminating the same variable, otherwise this technique won't really help us. So if I add equations 2 and 3, focus on my x's for just a moment, you'll notice that negative x plus 2x does not make 0 x's. So let's times equation 2 by a factor of 2 so that we get a negative 2x and a positive 2x. And I just write that by saying 2 times equation 2 in my direction. So hopefully that makes sense why I'm writing it that way. Carefully, I'm going to do it out loud with you guys. If I take 2 times the second equation, I should get a negative 2x for my first term, a positive 6y for my second term, a negative 2z, and then a negative 12. So that would be what I get if I times that whole second equation by a factor of 2. And then just simply carry down equation 3. No changes. Okay, cool. So let's go ahead and add those 2 up, and we'll arrive at a 5th equation involving just y and z this time. X's cancel. 6y minus 5y is just y. Negative 2z plus 5z sounds like 3z. And negative 12 plus 17 makes 5. And I will label this now as equation 5. Cool. So again, all of that work up front has given us a new system, a new simpler system, which I'll just rewrite one more time, kind of in more of a system way, meaning I'll just stack them on top of each other. So I'm just rewriting equations 4 and 5 that we just built together. And then from there we can use any of our prior knowledge. We talked about solving by substitution, we've talked about solving by elimination, we've even talked about solving through graphing. So take your pick. For this video, I'll go ahead and just show elimination because I noticed right away if we subtract these 2 equations, the y's cancel out. So I'll just dive in that way. You may have done something different, which is totally fine. As long as our solutions match in the end, that's what we care about. So if I take y minus y, again I get no y's. 2z minus 3z gives me a negative z. 3 minus 5 gives me a negative 2. So quickly dividing both sides by negative 1, we obtain a solution for z, which is just 2. Sweet. So as soon as you get one solution, things get to unpack pretty nicely from there. I'm just going to plug z back into, I'll go for equation 4. So I'll plug that solution of z equals 2 into, I'll choose the fourth equation. You might have chosen the fifth equation. And that will allow me to solve for y. So we're just kind of unpacking now our second solution. That gives me y plus 2 times 2 is equal to 3, or y plus 4 is equal to 3, so y is negative 1. Now we've got our second variable in this 3-variable system. So to get x, of course, you'll notice that with what's showing on the screen from our most recent work, we didn't have x involved. That was intentional. So to get x, we can go back to our original system and pick on equation 1, 2, or 3. Take your favorite. I'll go ahead and pick on equation 1. I like the looks of it because x is already isolated. So let me write some instructions for this next step. Let's plug y equals negative 1 and z equals 2 into our first equation, and that will allow us to solve for x. And I'm just going to rewrite that equation because I can't see it on the screen. So that was x minus 2y plus 3z is equal to 9. Does that look right? Looks like we got it. Okay, so I'll just plug in the negative 1 for y, the 2 for z, and we'll very readily have our solution for x here. So we get x plus 2 plus 6 equals 9, or x plus 8 equals 9, or x equals 1. So as we've seen, it's pretty typical to write our solutions for systems as ordered, in this case, triples, right? Our ordered pair language doesn't quite work because it's not just x comma y, it's actually x comma y comma z. So let's express our solution over here on the side as an ordered triple, and that would be 1 comma negative 1 comma 2. As we saw in our video from yesterday, this basically would refer to the point in space in the three-dimensional coordinate plane where these three different equations, which graphically appear as planes, intersect. So if you're interested in the graph, just shoot me an email. I can always send you the picture. Or maybe you want to try that cool GeoGebra 3D calculator for yourself. That's it for this exit slip.